Okay, so let's go over this first homework problem on the rate calculation. I'd say 25, 30% got it all the way right. Not easy to get this stuff exactly right. I think this is, I have commiserated with numerous other people in class, and we at least have agreed to accept each other's mistakes, and so we count that as the key. Okay, so here you go on the first one. This was input data or givens. On-peak contract demand 4,000, off-peak contract demand 4,000. On-peak billing demand for this month was 2974. Off-peak demand peak 3127. On-peak energy 401,639. Off-peak energy 1,061,470. 470. Recorded reactive demand lagging, which would be when the peak was set, would coincide with this number, was 2744.3 kVAR, and recorded reactive demand leading, which would be at a minimum demand point during the month, 1014.8 kVAR. Okay, so let's go down through the calculation of the bill. First two, pretty straightforward, just customer charge, administrative charge, so those add up to $23.50. On peak, this is the rate, and in the arithmetic, I guess I could have made this a little plainer, but it's this is H20 is the rate, and I7 is the amount, so that's the on-peak times the on-peak rate, 30,453.67. Questions? That one's pretty straightforward, not much to it. And then maximum, you just select the bigger of the two and multiply it by another $6.38. That's the rate. So this should be H21. Now, H21 is the rate. This is what? I8. So this should be the 3127 times $6.38, another $19,950.26. So those two added together would be the demand charge for that month. Questions? Okay, now a little more fun. We have the on-peak energy, which is, pretty straightforward. This is the rate, 7.44 cents, and this is on-peak energy, 401,639. So if you multiply those two together, you should get 29,881.94 on-peak energy. Okay, now it gets to be a little more fun. So we have to calculate the block size. And so let's see, where am I doing? There's the arithmetic. So if you can, it's hard to see, but let's see. So it's F26, the 200 hours, okay, times I7, and I7 is the on-peak demand. No, I7, let me see. That's 8. Yeah, the on-peak demand. So 200 times 2,974. But we're not done, because then we got to do this ratio. It's the off-peak energy, which is I10 for me. It should be this guy right here, divided by the sum of off-peak and on-peak. So that's those two together. That adds up to what? 1,463,109. Okay, so that's all of the arithmetic involved in determining the block size. Okay, there are questions on that? I know it's kind of, can you see it? Should I make it bigger? I can make it bigger. So if there's questions, it's probably on this. right here. So that's the block size. And then, so off-peak block 1, it's 4.94 cents. So these two guys multiplied together give 21,317.14. Okay? All right. Well, the arithmetic on the second block, and of course, you always have to make sure that you don't pay for more than you use. So, so right now, after I've paid this, I have paid for 431,521 of 1,061,000. So I have in no way paid for all of them. Okay. So then I go back to the arithmetic on the second block size is the same. So it's the next 431,521 kilowatt hours. Well, the rate goes down to 2.197 cents per kilowatt hour. So I multiply those together and I pick up another 9,480. Now I have paid for these two blocks, which is 863,000, but I used 1,061,000, so I got the rest to pay for, and I pay for the rest of them in this block. Okay, so what you can do is take that 1,061,000 and subtract off these other two blocks, and it leaves 198,428 that I haven't paid for, and I get to pay for those at 1.942 cents each. So I'll multiply that out. It's another 38.53. So you add up all of this, and that's the energy subtotal. On peak plus these three are the off peak. That's 64,533. Okay? Sir? I'm sorry, what? I could. Yeah, well. Okay, reactive charge. Okay, so they allow you power factor on the lagging side. They allow you the kVAR down to 95% on power factor. So where's my markers? What did I do with them? I brought them, didn't I? Oh, Lord, I got to use the markers in the room. Oh, that ain't good. We'll try. So, oh, it's a good one. Okay. So this power triangle would be for a power factor equals 95%. So this number of kVAR, they'll give you for free. Don't worry about it. It's on the house. Anything but your power factor, when you calculate this thing, your power triangle, what it comes out, what, 75%, something like that. But yours is all the way down here. So this power factor is about, I think it comes out 75%. Okay. So guess what? This amount you have to pay for. Okay. So the total amount of kVAR on the bill was right here, 2744.3. But the way the calculation works, and you see this on a lot of bills, if you take 0.33 times the maximum demand, that tells you the allowable kVAR. Or you can work through the power triangle, but that's the way the math works. So if you take this number times 0.33, you get this amount. And so that's the amount that they're giving you. So what is that number? That's 1031.91. So this is 1031.91. And this piece then is the, what was it, 27 something, can't remember all these numbers. I'm sorry. That's the, yeah, 2744.3 minus, so this is 2744.3 minus 1031.91. And that's what you got to pay for. And that is 1712.4. Okay. And you got to pay $1.46 each for those. Okay. So $1.46 times this guy, I-34. Yep, that's right. So that's $2,500.09. Okay. On the leading, you got to pay for all of them. They cut you no slack. And you know, that's a rip because leading helps them because everybody's lagging. And when you're leading, it helps the system. But they still, they don't care. Every dollar's green, right? If it's in their pocket, it's better than if it's in your pocket, as far as they're concerned. So they'll charge you another 156.87. So your total reactive charges are just these two, 3656.96. Questions? Cool. This, but this is based on the contract demand. So that's the rate. It's 93 cents, but it's 93 cents times I5, and I5 is right here. So it's 0.93 times 4,000. If you read that logic carefully, that's the correct. So the facility charge is $37.20. So if you add up all of those things that I have bolded there, you'll come up with 124,664.05. Take 1.5%, and the final bill 126,534.01. That's the smeared. That's the blended overall out the door. If you just take the total cost divided by total kilowatt hours, just to kind of get a feel for it. And for an industrial concern, that's pretty pricey. You know, I see a lot of them less than that. You see some more. Depends where they are. Okay. Now, power factor. Let's see. So the apparent, this is the hypotenuse of the triangle, right? So the KW is up here, and the KVA is this side, which is apparent power. And of course, that's the reactive side over there, which is the 2744. And so you just do Pythagoras, square those two, add them together, take the square root. And the apparent is 4160. And then you just take the KW divided by the KVA, multiply by 100 if you want a percent, and at 75.16 is their power factor for this month. And so you see their penalty starts at below 95. So yeah, they're in penalty. If they want to get out, they need to put on capacitors and reduce their kVAR. Okay. That's the penalty. I put it on here twice, I guess. And then the to correct, I guess I went back through. Is that the? Let me look at something. I want to see something. Point. Where's that 0.33? 1031. Yeah. I actually, instead of the 0.33, I actually did the power triangle on this one. It came out a little bit different, 1027. But anyway, this is the allowable. And let me see. What did I do? Well, let's see. So there's the demand. You divide by 0.95. That gives you the kVA. Then you use Pythagoras' theorem to get the allowable kVAR. We already had allowable kVAR up here based on this one. I guess rounding or something comes out slightly different, but it's pretty much the same thing. And so this is what's allowable. And so this is the 2744.3 minus this guy. So that should be, what have I got? G50. Where's G50? I'll find it here in a minute. Yeah, that's the kVAR for the month. And subtracting off, where is it there? Subtraction off G62, this one. So about 1716 is how much we would have to have corrected in this month to get to 95%. Okay? Questions? This is fair game on your upcoming quiz. I mean, I won't give you anything harder than this. I won't give you anything that you hadn't seen, but you ought to be able to run a few numbers, something like that. Okay? Very good. All right, well, let's see here. Which one do I want? Two. Sirs.
Just to get an idea would that be like you ask different parts of it, or are you generally?
Well, you know, that's a question. I've got to decide. These tests are harder to do with my bubble sheet. So I have to decide how committed I am to my bubble sheet. If I'm committed to the bubble sheet, then I have to ask you, you know, if you do that, it's got to be like an FE exam, you know, where you got a whole bunch of little, you got like 40 or so little calculations or questions where you can go A, B, C, D, E, or you can go A, B for true, false. You're pretty much limited. Now you can give a problem and say, okay, calculate the enthalpy of this and which one of these is closest to the correct enthalpy. So, and I haven't started on yours, so I don't really know yet. It's hard. It takes a lot of time to take a problem and put it in that format. So I don't know if I'm going to do that or whether I may just break down and just give you all some problems and just say, here, work them. You know, it's easier on the front end, but grading it is forever, you know. So I don't know. Oh, no, the test and quiz are synonymous. No. You've got enough on your plate in here. Well, okay, but I do have homework for you. Oh, that's right. Glad I do have 2 more homework problems. But you can turn, this would be to help you prepare for the test. So, I mean, you should turn these in at some point. I'm not in any hurry. You know how I love to grade homework, but you can turn these in, you know, in the next week or 2. But I think you should work on them. They're combined cycle kind of stuff. We've had a little bit of it, but I thought maybe you might want some more practice. Because anyway, so I'll just pass these around. Yeah. Oh, this, yeah, I can send you. Well, of course, what's the point in having you turn them in if I give you the solution? But that's fine. I don't really care. Yeah. Oh, these came out of the Thermo books. So I've got solutions to these. So yeah, I can send you out solutions to them. But anyway, go ahead and take these. But I suggest that you at least work on them without the solution, you know, to get some practice.
So we'll be during the test we'll work out some full blown.
You might, or you might have little pieces. I don't know. I haven't decided yet.
This is Tuesday, right? Next week?
Yeah, yeah, it's a week from today. That's correct. Okay, well, let's go ahead and look through these. Did y'all find these somewhat challenging?
Oh, yeah.
That's what I thought. They're pretty good though. So we'll, okay, so you've got the figures in front of you and all that. Okay, so on the first one, so we've got the Rankine cycle. And this one's ideal, okay? So you don't have to deal with the isentropic efficiencies. So that's nice. What do we got? We got 2 feed water heaters, closed and open. We got a high pressure turbine with no extractions, low pressure turbine with 2 extractions, and condenser and 2 pumps. So this is pretty much the Manila, you know, it's got what, reheat and 2 feed water heaters. So it's fairly long, but it's pretty much straightforward. And so there's the picture. So, you know, I guess the states numbers are listed. 8 high pressure steam. Yeah, you just put them on there. Back to the boiler, comes out of the high pressure turbine, reheater, pick up temperature, go back, partial expansion, extract at 11, closed feed water heater, extract at 12, open feed water heater. The rest of what's left in the turbine goes through to the end, condenser, pump, everything mixes together in the open heater. And then from here, we pump all the way through the closed heater back to the boiler. So that's not too bad. So here, we'll go through these state points. I'm not going to find, I don't have time to find all these state points. I believe these are correct. So if you have any questions on finding these. Now, I probably used an app to find these. So, you know, I like my little steam table app. And so they may not agree 100% with the steam tables, you know, if you do the interpolations, but they ought to be pretty darn close. That thing's pretty good. So let's just roll through and look at it. At 8, this is just superheated. So you should have an enthalpy someplace around 3583 and an entropy 6.68. So you can mark your own accordingly. So no extractions, we come straight out of the HP turbine, 1 megapascal. And, oh, that's S9. I can't read my own writing. So you see, because we don't have an isentropic efficiency, we keep that same entropy through the turbine. So we don't have to update it or anything, which makes the problem quicker and easier. So this same entropy at 8 is the entropy at 9. So you've got a pressure and an entropy. So you've got to go off to your steam tables and find that state. It's superheated and about 2821 kilojoules per kilogram. Okay, so we can go back up, see where we are. So we're through here. So now we're going to reheat. And so this will just be a lookup. And then we got 3 more states expanding through the low pressure turbine. So reheat exit, 1 megapascal, 500 degrees C, superheated, 3479 on the enthalpy, and the entropy is 7.7642 is my number. So then we go partially through that low pressure turbine to the first extraction. So it's 0.6 MPa and the same entropy because we're isentropic throughout. And so that's still superheated, 3308 about enthalpy. We get down to the next extraction, 0.2 MPa and the same entropy. So you're off in the steam tables again, superheated, about 3,000 kilojoules per kilogram. And we finally get to the LP turbine exit, 2 kPa, and again, the same entropy. And so now this drops into the dome, and so we have a quality of 0.92, about 9205, something like that. And the enthalpy is 2368. So the question is everybody comfortable with working through those and finding those enthalpies? If you have any questions on finding these, why don't you grab me after class, come by the office, and then we can go in and get on the board with some steam tables and play. So I'll be more than happy to spend, I mean, you know, by the time you graduate, you ought to be pretty darn competent in the steam tables. And this is a great, if you're not there, this is a great opportunity to get that done. Okay, condenser exit. So we've worked our way through 8, 9, 10, 11, 12, and 13. We're going to go to the condenser. Of course, what they don't show here is there most likely be lake water or river water or something coming in with a coil in here, you know, to carry the heat away to the lake so that we can condense it. Because this is still going to have a lot of steam. It's just really low pressure. And that steam has a lot of energy, but it's so cold we can't really do anything useful with it, so we throw it away. Okay, so this is going to be usually a saturated liquid state at this low pressure, and then we'll head through the pumps and the feed water heaters and all that good stuff. Okay, so there's your condenser exit, saturated liquid at 5 kPa. And there's an enthalpy. And we're going to use this specific volume for the pump work to do the pump trick so we can get the exit state out of the pump. And so that's what we're doing. So this is the inlet to the pump, and then this is the isentropic pump work. So we just added on to the enthalpy in, and this gives us the enthalpy at the exit of the pump. So this is specific volume, meters cubed per kilogram, and then this is the pressure difference. And what is this, kPa? Yeah, because it was 5, it's 5 kPa. So if you use the kPa, you don't have to do anything to the units. But you got to always be careful when you're doing this pump trick that you get your units straight, okay? So anyway, so this is the inlet enthalpy. It's about 0.2 is what gets added. So you add these two together, and that's the exit of that first pump. Are there questions on that? Okay, and then the only other adjustment would be if it's not isentropic, we would have to divide this little piece by the isentropic efficiency of the pump to account for that. But we don't have to do it in this problem. Hmm? Yeah. 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 This term right here, this term is the isentropic pump work. And so let's say that pump was 75% isentropic efficiency. You just divide this by 0.75, and that makes it bigger based on the inefficiency of the pump. Yeah. Okay, let's see. Open heater. Let's see. What are we told? I'm not sure what are we told on the open heater. Let's see. Steam is extracted. Extracted steam leaves the closed. Yeah. I'm not sure. Let's get on down. Oh, I can't keep all this stuff in my head at one time. Let's see. Leaving open heater, assuming saturated liquid at 0.2 MPa. Okay, so that would be open heater. That has to be here. So this open heater the pressure in here is assumed to be this extraction pressure. Okay, so that's, unless you're told something different, in these problems, we usually don't account for any pressure drop. So that would be the extraction pressure here. That would be the pressure throughout this feed water heater. On this closed feed water heater, the pressure on the shell side in here, on the outside of the tubes, would be the extraction pressure at 11. And if this is, it's common to assume that this is saturated liquid at 6 is saturated liquid at whatever pressure this this extraction occurs at. So that's pretty common stuff. So leaving the open heater, saturated liquid at 0.2. So that's pretty simple just to look up. And I got specific volume because then that's the inlet to the pump. So we got another pump that's going all the way, and this has to go to boiler pressure. Okay. So this pump will be a little more on the work side. Okay. So it's the same game, the pump trick. The entering enthalpy, which we found right here. And then we add on to it specific volume times delta P. And again, if you write this in kPa, you don't have to worry about units. Neat little trick to remember. Okay, so the pump work portion is 15.7. Add it on to the entering enthalpy, and we get 520.4 coming out of this second pump going. That's at 4. Now that's not 5, but that's coming out of the pump. Okay, let's see. So closed feed water heater exit, compressed liquid. It says, oh, consider it to be the saturation temperature at 6 bar, and that's the extraction pressure. So this is operating at 6 bar. It says, okay, whatever that saturation temperature is, we'll assume that we got this feed water up to that temperature. In reality, it wouldn't be quite that high, but we're still kind of doing, okay. So that's compressed liquid. I got an enthalpy of about 679 out of that. Condensate from closed heater is saturated liquid at 0.6 MPa. So that's just a lookup, saturated liquid at a pressure. And then this is the trap. So this is just a throttling process. This is the easiest one on there, because if you know 6, you know 7, because the enthalpy is constant across a throttling process, except for changes kinetic potential energy, and we're throwing that away. So if you know H6, you know H7. So that's pretty easy. All right. So there's this. Okay, so we have all of our enthalpies. Once you got those, then you just got to start doing your energy balances. If you have more than one heater, always go to the highest pressure heater first, because this will involve only one extraction. If you go to this one first, you wind up with 2 unknowns. And then you got to go solve the other one first. So, okay. So the extraction is, the symbol for that fraction is, we're using Y. Okay, so we're going to have Y times H11 coming in. This is all of the mass is put back together here, so that coefficient is 1 plus 520.4. That enthalpy is equal to Y times 670 plus 679. Okay, any questions on doing that energy balance? Yeah.
If you, so like had some lines that said makeup water is added here. Is that just an additional mass fraction?
Yeah.
you have to account for? But it'd just be like Y triple prime or something?
Whatever it is,
That's
you know,
what
based on how you've drawn your cycle.
you have to just solver it. Or something.
Well, you probably,
Probably know it.
yeah, you would probably have extra information. Because that's not gonna, you know, that's, because you see, if you've got makeup water, that says you're not returning all of your steam, and so, or that's blowdown, and so, you know, you can't, your condensate coming back will not be as much as went out. Or the feed water that goes in the boiler, what you're saying, if it's blowdown, you're taking some of that water and putting it down the drain. So, you know, you've got to have information on that. Yeah. Well, see, you know, in the other course, we use the modeling software, and see, it does that all for you. You just put in a blowdown amount and it handles it, which is nice. Yeah. Okay. So this is what the summation of the innies is equal to the summation of the outies. And you factor out the y's and bring them over here and solve. And so you get about a little over 6% is what's extracted at that first extraction point right here. Okay. All right. So then we're on down to the next. So then we got a balance on the open feed water heater. So this is H12 times Z is coming in. This mass fraction this is what's coming out of the condenser. This is 1 minus Y minus Z times 137.95. And this is what's trapped back from the closed feed water heater that comes back. And so this mass fraction is Y. So this is Y times 670. It's all put back together here. And so this is a coefficient of 1 times 504.7. And so there you go. Yes, again, summation of innies equals summation of outies. And then, you know the Y, that's 0.06013. So you substitute that in, do the arithmetic, and Z is 0.117. A little bit of work, but conceptually, it's not all that bad. Okay. Thermal efficiency. So we got to get the turbine work, and then we got to subtract off the pump work. So for the high pressure, we've got the entire mass flow through the high pressure. So that coefficient is 1. When we get down to this low pressure now, we've got the entire mass flow from 10 to 11, but we've lost Y. So this is going to be 1 minus Y from 11 to 12. And then from 12 to 13, it's 1 minus Y minus Z when we write the equations. Okay, is everybody good on that? You just got to kind of get the hang of it. And, let's see, so where are we doing here? Someplace, thermal efficiency. Okay, so here's the high pressure. I broke this off and just did it. Mass coefficient of 1, just enthalpy difference right there. Low pressure, so mass coefficient of 1 times this, there's 1 minus Y times H11 minus H12, 1 minus Y minus Z times H12 minus H13. Plug and chug, low pressure, 980.6. Add them together, we got what, 1742.8 kilojoules per kilogram. Okay. There's the pump. Again, don't forget mass fractions on the pump. So this first one is just what's out of the condenser. That's 1 minus Y minus Z times that enthalpy difference. And we've already kind of done this. But so there was the enthalpy. So when you do the arithmetic on it, you get 0.165 kilojoules per kilogram, not much on this pump, not a big pressure difference. Pump number 2, all the mass is back together, so we get the full enthalpy difference, and that was 15.7. So you add those two together, you get 15.87 kilojoules per kilogram. So net work is total turbine work minus pump work. Comes out 1726.9. Boiler heat input, we got the main steam, we got the reheat, but it has full flow, so it's just the enthalpy differences. So it comes out 3562, and so there's your cycle efficiency, about 48.5%. Net power output, oh, okay. So we've got, 42 kilograms a second, and this is the net power in kilojoules per kilogram. So that's 72,531 kilojoules per second, and a kilojoule per second is a kW. So it's 72.53 megawatts. Okay, everybody good? Okay, let's do one more of these. I know it's kind of tedious, but I kind of think we probably should do this. Let's see, that's number 2. Number 2 was a little bit of a different ilk, as they say. Okay, so let me make it a little smaller there for this. Okay, so that's what we got. So we've got a gas turbine, compressor, combustion chamber, compressor, combustion chamber, gas turbine, and then we come out of there, and that's the energy source for the steam cycle. And we've got this, our heat exchanger is our boiler, and so we're generating main steam, and then we're doing some reheat after a partial expansion back into the turbine, and then we come out to a condenser and a pump. So this is a little bit of a strange device here. So we'll look at it. Well, so there's some of the details on it. You know, pressure ratio, 7. So that's the discharge pressure from the compressor divided by the input pressure, and then it goes the other way across the turbine. Air comes in 15 degrees C, 10 kilograms a second. We're heating coming out of the combustor at 950. And the heat exchanger exhaust is 200 degrees C, so that's right here, coming out at, what is that, 11. Okay, on the Rankine cycle, main steam pressure 6 megapascals, condenser pressure 10 kPa. We do have steam flow rate through the whole system. There's no extraction, so it's constant at 1.15 kilograms a second. High pressure turbine exit, 1 megapascal, and the reheat steam is 400 degrees C. Isentropic efficiency is 80% for all pumps and turbines. Okay, so, well, with all of these things, you got to go find the enthalpies. That's the first part of the game. Got to find the enthalpies. Well, so when we have air, we can use this reduced pressure. Or is that relative? I always get those confused. Anyway, it's that piece of bar that's in the air standard table. And so this pressure ratio is equal to this parameter that you can look up in the tables, okay? And you can, this is a function of temperature as well. So this is the little equation that we use. And so, but we look up this parameter based on temperature. And so you see here at this first state where we're 15 degrees C, but the table is in Kelvin. And so 273 and 15 is 288. And so here I am interpolating. At 285, it's 1.1584. At 290, it's 1.2311. So when you do these, man, you better get your interpolation hat on because you do a bunch of it. So this gives us PR, and then looking at this relation, then I can solve for P sub R8 by just multiplying this one by 7. And so this is for isentropic. Now this is the isentropic enthalpy that you then have to adjust it based on the isentropic efficiency. Okay, so then the P sub R8 is 8.41414. And so then I'm taking that back into my table and interpolating to get the enthalpy at 8S, which comes out 503.072. And then this is the equation for isentropic efficiency of a compressor. And so you put the isentropic up here, this is the inlet, and you solve this for the actual exit at H8, and it comes out 556.8. Okay? So we found one state. So now we get to do the combustor. Well, the 556.8 is in, and here we're given if you're given a temperature, then you just go find it, okay, in the ideal gas or air standard table. And so it's 950 C plus 273 is 1223, and this is the interpolation. So from 1220 to 1240, and this is the P sub R value is 256.02. I don't know if we need that or not, but if we do, I found it. And the enthalpy is 1303. So coming out of the combustor. Okay. Oh yeah, we do need that. So then we go through the gas turbine. And so now I take this P sub R value going in, and because the pressure ratio here is 1/7, because we're going back to atmospheric basically. So you divide that by 7, you get 36.574, and you go back and you're interpolating again. So here's the PR values. The 36.574 is in between. We're interpolating, and this enthalpy, and this is an isentropic, so this is 10S. This is isentropic again, 726.739, and then this is the isentropic expression for the turbine. So you plug in here and you solve for H10A, which is 870.8. Everybody good? All right. So now we get to start to have some real fun. So we look at the heat exchanger. Well, so this hot air coming in at 10 is transferring heat to the steam or to the water, whatever the state is in, and that's what's producing the steam flow. I've got from 2 to 3 going this way, and I've got from 4 to 5 going this way. But the hot air is providing all of the energy for this. And so you can do an energy balance. So M dot A is equal to H10 minus H11, or M dot A times that is equal to the energy picked up by the steam. So that's M dot S, which is the constant for both of those flows. So I factor it out. H3 minus H2 for this flow, and H5 minus H4 for this flow. So that's our basic energy balance on the heat exchanger. Now let's see, we got to deal with the steam states. So some of them we know. So we know the state 5. Let's see, let's go back up and look. I get lost in the numbers. So what do we have? So our first steam is 3, comes out at 4, gets reheated, comes back in at 5, and leaves at 6. Okay. So the stuff we know the reheat steam at 5 is 1 MPa, which is 10 bar and 400. So I can look this up. I know the low pressure turbine exit going to the condenser. And let's see. So for the, let's see, so the isentropic expansion, so 6s would be equal to 5 back up here, because of course we got to be careful because this is not an isentropic turbine, but we had the information to get 5, and so we can use that entropy to find 6s, and then we can use the isentropic efficiency to find 6. Okay, so that's what we're doing here. So 6s is equal to S5, and there's the number, 7.4651. And so this is at 0.1 bar. This is the entropy of saturated liquid, and this is saturated vapor, and this is saturated liquid. So we calculate the X. So the quality for the isentropic state 6 is 0.90866. So that makes the isentropic enthalpy at 6, just using that quality, saturated liquid. That's enthalpy of vaporization. So we get 2366. And then we use the isentropic turbine equation set at 0.8 to calculate the actual enthalpy at 6. 2545.6. What is it? Oh, I just went ahead and I went ahead and calculated the moisture. I guess I already. What? 2545. Yeah, this is the quality at 6 coming out of the turbine. So anyway, just I don't know if it asked for it or not, but I went ahead and did it. So coming out of that turbine, we've got 1.63% liquid going to the condenser. The rest of it's low pressure vapor coming out here. Sometimes they don't ask for that. Sometimes they do. Okay. So then the condenser exit, that's just a lookup, saturated liquid at 0.1 bar. That's easy. The pump exit at 2. So this is specific volume times delta P, and now I'm dividing by 0.8 because that's the isentropic efficiency of the pump. That makes the pump work a little bit bigger. Again, if you use KPA, the units take care of themselves, and so this pump work is 7.56 kilojoules per kilogram, and then I can add that on to this enthalpy out of the condenser, and that gets me the enthalpy out of the pump. Okay? Everybody good? All right. Heat loss. Okay, so this is on the gas side. This is the mass flow rate of the gas. This is the enthalpy difference. So this is the amount of energy that hot gas stream out of the gas turbine is dumping into that heat exchanger that is absorbed by the 2 steam flows. Okay? And so I'm just going to set that equal to the equation on the steam side, 1.15 kilograms a second. It's H3 minus H, whatever it is. Let's go up and look. Okay. So H3 minus H4, and then it should be H5 minus H6 on those. 2. H3 minus H4. That's H. Is that right? Oh, surely that's right. Something don't look right there. Let's go back up and look again. Surely. Sure, don't, oh Lord, don't let me have a mistake in this thing. Three minus 4 and 5 minus 6.
both of the entries and then both the exits?
Are we looking across the heat exchanger? I did it across the heat.
Oh,
I could have done it.
this is the heat ex, thank you, thank you. This is the heat exchanger. Whew. Thank heavens, okay. There we go, okay, all right. So this one, yeah, so it should be 3, because this is we're coming through this way, so it's 3 minus 2, and it's 5 minus 4, thank you, thank you. Too many numbers. Okay, so 3 minus 2, 5 minus 4. Okay, and we have numbers for these. Okay, great. I was pretty sure I had this right, but it's hard to remember all this stuff. So if you do the arithmetic, you can boil this down, and this is actual. These are actual states, okay? So you can solve for H3 minus H4 actual, and that has to be 374.034. And then you can solve for the isentropic, right? So if I take, use the isentropic efficiency, then the isentropic work, I can divide that by 0.8, and it's 467. Okay, because say I've got 2 unknowns here, and the only way I figured out how to do this was to guess a temperature. And so I said, okay, I'm going to guess 500, and then I'm going to evaluate H5, and then I'm going to evaluate the isentropic 4, and I'm going to calculate the isentropic work. Okay, and so if I guess 500, the work comes out 502, 503, it's too high. If I guess 400, it comes out 420, not high enough. So you make a couple of guesses, and if you guess 456.6, it comes out right on the money, and so that tells you that's the right temperature. Okay. And so that lets me find state 3, because then I have a temperature and I have a pressure. So let's go back up, find state 3. Say, so that's the main, what I would call the main steam flow into that's the high pressure flow into this turbine. So then you've made everything balance and you've found that temperature. So somehow I'm sure there's other ways to cast it, but that's certainly one way. Okay. And then, you know, once you have that, then you can find state 4, because this would be the isentropic expansion, and then you find the actual. And so then it just kind of falls apart. So there's your actual turbine work. Yeah, that just shows that it works. That's the number that we had calculated before from the energy balance. Okay. Oh, I think it did ask for the moisture. So I had already calculated this previously at 1.63% moisture. Steam temperature at high pressure turbine, 456.6. Gas turbine work, 10 kilograms a second times the enthalpy difference across the gas turbine comes out, what, 4322. That's kilojoules per second, which is kW. Steam turbine, there's your mass flow, enthalpy difference across the first expansion and then the second expansion, 1256. So total power is the sum of those. Pump work, enthalpy per kilogram times the flow rate, 8.7 kW. And compressor work, the 10 kilograms a second times that enthalpy difference, 2686. Just look at the huge difference between the compressor work input and the pump. Easy to pump a fluid, hard to compress a vapor. Okay. So combining them, this is the gas turbine plus the Rankine cycle power, 5578, almost 5579 kW. This is the pump taken off, This is the compressor taken off, so we net 2883. Combustor heat input, mass flow rate times enthalpy difference, 7463 roughly. So then the efficiency comes out about 36.64%. And the net power is 2.9 megawatts. Okay. Whew, this is mind numbing. Okay. Why don't we just skip the other and do something else? Is that good? I don't know. I might. We'll see. Well, you've seen it.
Yeah, but you made something slightly different for easier.
Yeah, we'll see. Say if I distribute it too greatly, then I can't use it because you guys give it to all your buddies, and then nobody will work on it because they already have a solution. They just write down the solution. So I'm not so sure I'll send this one. But if you, I mean, you can come by the office. You're welcome to. Maybe I'll post it in a display case. Then you take pictures of it though. I know y'all. I don't know. Let me consider it. All right. Okay, let's see. Let's do something else. Get rid of this. All right, I guess I'll have to open it. Oh no, we sure don't want this. Scan material. Okay. Now, I'm embarrassed to say I haven't written PowerPoints. These are my old notes, my old yellowed notes. And so this is going to start the next block of the course. And I could copy these, and I don't mind handing these out. They're pretty rough and they're scratched up, and so I don't know. Why don't we just go slow, and you can take whatever notes. But normally I would write this on the board, but if I write it on the board, it doesn't get captured in the video, and so I'm kind of between technologies here. So this is actually, for steam is a wonderful, water is a wonderful fluid, okay? It's been called God's gift to heat transfer. Steam is really, really good. And so, well, why do we use it? We use water whenever we can as a working fluid. So, well, high heat capacity. So heat capacity is what? Specific heat. Where did I do that marker? There we go. So 1 BTU per pound mass per degree Fahrenheit. So if you get a chance, you ought to get in the back of your Thermo book or get online and just search on specific heats. See if you can find anything that has a greater specific heat than water, that's cheap, that changes phase, and all the stuff. Pretty darn good. I mean, it's virtually, you have to pay something for it, but compare it to oil or something. Pretty cheap, So it's high heat capacity, cheap, abundant, and non-toxic. And you can probably come up with some other characteristics. So water is pretty ideal. Okay. Now, one of the issues is that you have to get it pretty hot. We have to work at pretty high temperatures in order to get, high pressures and superheat it and all that sort of thing. Okay, so we wind up, pretty darn hot. For waste heat recovery, there's organic Rankine cycles. Somebody have organic Rankine cycles as your topic? That one nobody selected. They use like refrigerants, refrigerants are expensive. If they leak, they could easily be toxic, or you certainly wouldn't want to breathe them. You wouldn't want to bathe in them or something like that. So, but they boil at much lower temperatures. So sometimes for specific heat recovery type applications, we use some other things. In terms of power gen flow rates, oh my goodness. That Cumberland, TVA Cumberland, those things are, I think, 1,300 megawatts. The steam flows up there are someplace in the order of 10 million pounds an hour. That's about the biggest unit I've ever taken a look at. But you also have small process heating boilers. You can buy a little process heating boiler. You can sit in that little corner over there. It'll make steam. It could be 1,000 pounds an hour. So, flow rates can be all over the place. And as far as steam conditions, from utility sector, we have what? We have supercritical, units, and we have subcritical. Kingston, 1,800 PSIG. So a lot of other TVA plants are 2,400. Other TVA plants, 2,400. Bull Run, which they are in the process of shutting down if they haven't, was supercritical. It was someplace around, 4,000, something like that. You see critical pressure up there is what, about 3204. So that's that ISO bar that goes through the top of the dome. So if you got a TS, what, you got that ISO bar that just touches there, comes down like that. That's 30, what is it, 32, I can't remember, 3204 PSI. So the pressures above that, you don't interact with the dome on the heating cycle. Your pump pumps it up to a high enough pressure that when you heat it, it just is steam. It doesn't go through that boiling transition. And you also see critical temperature. There is 705. That's the saturation temperature at 3204. And you pick up, you pick up efficiency. You pick up lots of efficiency at higher temperatures, higher pressures, but that's why we went through all that Rankine cycle stuff. Well, fuels, you guys are now kind of experts on that. You got your coal, you got your natural gas, you got your nuclear, you got potential solar, for a thermal source. Any sort of a thermal source, you can have, wood, biomass, wood waste, bagasse. What's that? What's bagasse? You know what that is? We got Cajuns in here. Everybody from Louisiana? Well, ask her what that is. I bet she knows. That's what's left over when you process the sugar cane. That's the hulls and stuff. So down there they make, man, there's lots of that stuff. And it can be burned as a boiler fuel. Corn husk, all kinds of stuff. So, and you know, that's another reason why we spent so much time going through Rankine cycle, is all of that stuff is just a heat source that can be transferred in to make that steam. And once you get that steam, hey, you're doing Rankine cycle. So it's pretty fundamental to what we can do. Anybody co-op in a paper mill? How many different energy sources did you deal with?
I had one was like a recovery boiler that generated this thing, they called it a black liquor.
Yep.
Part of they shot that in there and burned it, and that's what made the energy to keep the steam.
That's right.
And then they purified that chemical by burning it, and then they recirculated it again.
What is that? Oh, I'm supposed to know what that chemical is, but yeah, paper mills. What? So you buy a tree and you chip it up. Got these big hogs. They call them hogs, and they eat up trees and make wood chips out of them. They take that and they soak them in green liquor, and the green liquor dissolves the lignin, and basically it makes it just kind of dissolve, and you get the pulp. And then they take the pulp and they process it into paper, and eventually they spray it out on rollers, and it's an amazing process. Well, and so after you soak the wood chips in the green liquor, I don't know, I've never seen, does it change color?
It's actually like by the time it goes into the boiler, it goes through like 6 different like condenser heat exchangers, and it's like tar.
Okay,
It's like really
okay. And so they take this stuff, and I guess they, like Casey's saying, they drive off a lot of water, you know, to concentrate it. And then it's a fuel, and they burn it again, and they take the ash, and they make green liquor out of it again, and it just goes around and around and around in a circle. So that's pretty cool. And then they've got all this wood waste around, and so they typically have wood waste boilers to make more steam. And then I guess natural gas is probably the last resort, because because the wood waste is free, the black liquor is free, except that, you know, they have to use steam to drive the water out of it to concentrate it so that you make it so you can burn it again. So paper mills, they might not smell the best, but they're really energy-wise. They've got all kinds of different pressure levels, and they're very energy efficient. They don't vent flash steam. You know, if they have a high pressure condensate, they'll drop pressure on it. Some of it will vaporize, and they'll take that vapor into a lower pressure header, and they'll use it. And they keep flashing the steam as the condensate pressure comes down. And they're very efficient. A good paper mill is really an incredible place for a thermal science person to work. It's pretty neat. You know, I've got a big PDF file from the government. I might just email that out to y'all so you can, just on your own time, you know, enjoy reading about it. Let's see. We were at City of Lebanon recently, and what they have this, it says this is cogen. Yeah, they've got a little cogen set up. Oh, I need to pull up some slides on this. So what they're doing now is they're burning natural gas, but what they're just getting it up and going. What they intend to do is burn the sludge out of the wastewater treatment process. So, you know, so they come in, so, you know, all the sewage, all that comes into the wastewater treatment plant, and they purify it. They take all that stuff out of there, and they basically concentrate it. Right now, they're taking it to landfill. It's costing them, I don't know, hundreds of thousands of dollars a year to get rid of the sludge. Sometimes you can take some of that sludge and put it on fields for fertilizer. And it also, if you dewater it enough, you can burn it. And so that's the purpose of this facility, is to, you know, burn this sludge along with some natural gas to make some electricity and to generate some heat that they can use in the process. So it's been there 3 or 4 years and they still don't have it quite working. I don't know. We talked to the guy when we were there and he was confident it was going to happen, but they're still having to pay to get rid of a lot of sludge. And the idea was they're going to burn it, you know. So, and you can burn all kinds of stuff in the right kind of boiler. But say, so that could potentially make some air emissions, but it would keep all of this sludge out of a landfill, or a lot of it. So, you know, kind of like, then you got to try to clean up the emissions, you know, so it's not easy to do. So, okay, so we talked about size range on the units. Well, let's see, let's just always want to design considerations. Oh my goodness. You know, if you're going to design a boiler or a steam generator, whatever terminology you like, these are just a few of the things that you have to consider in order to produce a system that is going to make people happy. You know, you got to supply the steam, most economical package, fuel characteristics. What are you going to burn these days? You know, back in the day, coal was probably more of an option. There's probably not many people putting in coal today, but if you're going to burn coal, then there's even different types of technology. There's what they call stoker spreader type boilers that burn chunk coal. You can have 1 to 2 inch chunks. You just dump them out on a conveyor. It rolls into the to the firebox and burns. TVA uses pulverized coal. So they take pulverizers and they take this coal and they grind it up to the consistency of face powder. I mean, they'll get, when we make the trip, they'll set a big jar of this black dust, you know, hopefully nobody will drop it, but you just shake it around and it looks like it's just powder, you know. I mean, it's like, I don't know, 2 to 4 microns, something like that. And they have pulverizers that it makes it easy to transport, makes it easy to burn. So, you know, how are you going to handle the fuel? What about transportation? How are you going to, you know, like if you have coal, are you going to bring them in on trucks? Are you going to bring it in on rail cars? Are you going to bring it in on barges? You know, how are you going to get it there? How are you going to offload it? Where are you going to store it? How are you going to transfer it from the coal pile and actually to, you know, to the pulverizers, and then from the pulverizers get it into the burners to actually burn it. There's a lot of things to be considered. Fuel, easy, natural gas. Now, natural gas is a piece of cake, man. Build your plant by the pipeline, hook the pipe, pressure reduce it down to the burner pressure, blow it in, burn it. Life's good. Whole lot easier. In the old days, though, gas was pretty expensive. Yeah, you know, back before fracking, that gas was probably $6 to $12 a million BTUs, and coal was $1.50 to $2 a million BTUs, and that's why so much grew up around coal, because it was by far the cheapest energy source. And then along comes fracking and turns this thing upside down. Okay, that's a good place to stop. So we'll continue on with this next time. I might go through that last problem. I just couldn't do 3 in a row. Whew, too much.